Hi, everyone, and thank you for joining our webinar. This is the first episode in our Sync with an Expert series. I'm Patrick Bark, the Customer Experience Marketing Manager with Safran. Today, we'll be discussing choosing your Safran Timing Solution. First, we'll have a presentation with our team of Safran experts. We have Ron Dries, Solutions Architect and Systems Engineer, and Dave Sohn, Senior Solutions Architect. Following this presentation will be our live Q&A segment. We collected a number of questions in advance from each of you that will be discussed, but you also will have access to the questions tab at the bottom of your screen to submit any questions that come up throughout the event. Some questions may require more in-depth responses, so may be followed up after the event. There will also be polls presented throughout to help us understand each of you a bit better when framing our answers for the Q&A section. And finally, if you're disconnected at any point during the event, you can simply use the same link you used to get here to reconnect. And as always, we will be recording the event for our on-demand version, which will be available following the event for anyone who is unable to attend. This version will be automatically sent to registrants who did not attend, but will also be available on our event webpage for anyone who has not registered yet. Once again, thank you so much for joining, and at this point, I'll pass it over to our presenters.
Thanks, Patrick. I'm Dave.
Hi, I'm Ron. And today we're welcoming you to this presentation on how to choose a Safran timing solution. When looking at our timing solutions that are available, they're highly configurable and modular. They can be used in many different applications that need timing, from public safety to data centers to communication. Safran has timing experts that are here to help. Dave and I are here to dive into some of the more technical aspects of how to choose a timing solution to meet your needs. We're going to start today by going over some definitions of how the products can fit into a network architecture. Those three different levels that we'll talk about, and then you will see how the products fit into them are the reference layer, the distribution layer, and then finally the end node or end user layer. So at the reference layer, that's where we were talking about consolidating references into one point, and then being able to feed those references to devices in the distribution layer. That is also where we will have our redundancy for feeding into the distribution layer. And then once the reference is passed to the distribution layer, that's where it will fan out to other distribution nodes, and finally to the end nodes.
Yeah, so as Ron said, in the reference layer, think of that as where you get and combine all of the references that are available to you, your primary references, any of your failover references, and get a single solution that then you can pass down into your distribution layer in order to get to either all the end pieces in your system. It might be across an entire site, like a data center. It might be across a campus where you may have multiple buildings. It might even be site-to-site kind of distribution. But also at the reference layer is where you can, and there's resilience built into all of this. At the reference layer, the resilience with the multiple potential references into a single device, but you can also have resilience by having multiple devices at that reference layer, which may be locally together, or it might be a combination of locally together and at different sites. And then the scope of that distribution layer is really determined by the number of end devices you have and the scope of that distribution, whether, again, it's in a single kind of system that may have many endpoints that need to be fed, or you're actually distributing over a wide area that has a lot of different endpoints.
All right, so now that we've covered some of that, we would like to then go into the products themselves, and then how you would choose between which of the products you need. Now, the applications are always varied. How all of these pieces will fit together will always depend on external factors and things like that. One of the main things that we'll look at today is from the end nodes, and what the timing accuracy is going to be needed at the devices that are consuming the time. So domain controllers, switches, those things. And those one of the major differences between when you're looking at a secure sync versus a White Rabbit. When White Rabbit is needed, that's usually when we're talking about needing sub-nanosecond accurate timing to those end nodes. The secure sync or VersaSync product lines are going to be more for legacy timing signals, the reference layer, so synchronizing to GPS, and then outputting several different timing references to other devices that need to consume it. The secure sync, VersaSync are similar, but they also have their differences. We talk about either of those. They're the same timing platform, same configuration. They fit in different environments. The secure sync being a 19-inch 1U rack mount device versus the VersaSync being a small form factor rugged device. Although both have their own, share the same timing platform, the VersaSync is typically seen in more mobile rugged applications where the size, the weight, power are constrained, and those applications require low size, weight, and power. Secure sync fits better into applications that have rack space, higher power, maybe redundant power systems, and things like that. Am I missing anything?
Well, so one of the common elements between our secure sync and VersaSync is the modularity that's built in both in the hardware and the software, but they're kind of delivered differently, as you were talking about, with the secure sync being a rack mount box that is probably more suited to a data center environment, in a shelter or something like that, where VersaSync, as it says, it's smaller, lower power, it's more rugged, and it's more for harsher environments, mobile areas where those constraints are important. Now they both have the modularity, with the secure sync being much more hardware modular, where we have option cards that are installed in order to gain access to different types of inputs and outputs in the system, whereas the VersaSync is more software modular, where you have a sort of fixed input and output array that then you get to select and choose in the software the kinds of inputs and outputs. Now, when you're selecting these things, we talked about legacy outputs. That's, we say legacy, but really what we mean are non-network, right? So everything is kind of moving towards network timing and such. And so where we say legacy, it's everything before the network, so that's our PPS signals, our frequency outputs, iRig, HavQuicks, the wide array of inputs and outputs that are then available. One thing especially, it will kind of go a little bit into another part of the difference between the secure sync and VersaSync in that hardware modularity. That's kind of the first key point of selection of the unit, which is the chassis type. So in our secure sync, based on your current needs and what your future needs might be, you have to choose, do you want a 2-slot option or a 6-slot option? And that's the number of option cards that can be installed in a single unit. What's nice is those can be factory configured, meaning we install it for you when you order it, and that way you can get exactly what you need at the time of order, that configurability. Or we have option cards that you can field install, and so that allows you to have your current configuration, your current needs, and still think about the future of what you might need to add on later. And that's where the 2 versus 6 comes in, is kind of your mindset on how much expansion you might need and how much you want to future-proof that capability. Then the next big thing that comes in, which is probably what we get the most questions on in selection, is on the oscillator types. And there are common elements between secure sync and VersaSync, but Ron, why don't you go through a little bit on the oscillators that we have available?
Absolutely. So for the secure sync, we have 5 oscillator types. They range from the TCXO, temperature-controlled oscillator, the OCXO, an oven crystallized oscillator, a low phase noise OCXO, rubidium, and then finally the low phase noise rubidium. On the VersaSync side, there are only 3 oscillator choices. They're the same OCXO and low phase noise OCXO, but because of the low size, weight, and power requirement of the VersaSync, instead of the rubidium, we have the MRO, or the mini rubidium, micro rubidium, mini rubidium. It's a smaller version of the rubidium oscillator, provides similar rubidium type characteristics in a smaller form factor package. Looking back at either of those options, the main thing that you would look at when choosing an oscillator type is its holdover accuracy. There are several factors that come into that, generally based on the application that will drive that choice. Those choices is really how long the device can run without a reference, without somebody being able to go in and synchronize that oscillator. We have some use cases that the devices are installed remotely. It takes several days to get people out to the site to remedy an antenna issue or a power issue. And in those cases, they want the product to be able to run for a long time without drifting so much in time error. That's usually where we'll look at the rubidium. We don't typically talk a lot about TCXOs, but we do still offer those for applications that are cost sensitive. So much like Dave was talking about with the chassis types, the 2 versus 6 being a cost savings, the TCXO would also be a cost savings. Our standard unit that we provide is an OCXO unit. It gives you decent holdover and accuracy for the money at that point. And then when we go into talking about low phase noise, those applications will usually know when they need low phase noise. But the low phase noise OCXO actually gets combined with the rubidium to create our rubidium low phase noise option. And in that case, it makes sure that there's not so much of a swing in our frequency or our phase error over time. And I'm sure I probably missed something in there, Dave. So,
well, so I mean that was great, Ron. So the first thing that generally think about with the timing is the holdover, and that's a huge impact in the oscillator selection. Beyond holdover, one of the next biggest pieces is phase noise. And you might say, well, why didn't I talk about actual accuracy? Yeah. And that's because, except for the TCXO, generally speaking, the differences between accuracy and the OCXO, low phase noise OCXO, rubidium, low phase noise rubidium, and the options on the VersaSync are not so different in terms of accuracy while you're synchronizing to a reference. Yes. Really, the major part that affects the accuracy is the type of reference that you're synchronizing to. But holdover is really key on the oscillator selection. The other piece that really comes into play is temperature. So temperature is really the biggest environmental effect on these oscillators. And as you get into our higher quality oscillators, they're less impacted by temperature. Now, while you're synchronizing, that's not a big deal, because as you're synchronizing, part of that synchronization will account for those temperature effects that are happening, during the day. Maybe there's a cycle, let's say you're in a data center, there's some cycling during the day based on heat load on the building or whatever. But in holdover, once we have no source to synchronize against, now the temperature will directly impact the quality of that holdover. But the next piece that we keep talking about, we haven't really defined it, is that phase noise. Yep. And phase noise is really the purity, the quality of the frequency output that you're getting from the device into your end system. Most people, as you say, know when they need that improved phase noise. Some applications are really concerned about that. Communications is one of those. On the defense side, radar applications. It's really kind of where the frequency is being directly used or used as the basis for, let's say, an RF signal that's being, a carrier that's being used for something else in communications. And the improved phase noise means improved bit error rates, for example, on communication. In radar application, it would be improved target acquisition or tracking, or the coherence of the target that you can see. In other areas, it might be where you're doing frequency overlap, like in some of our public safety applications. The better signal allows you to better distinguish between those as you're doing overlaps across that application. And so there are unique effects as we go across the oscillator, and then there are combination effects, you said, like the low phaseness rubidium, where that's actually combining the benefits of the holdover from the rubidium and temperature effects with the low phase noise outputs for those specific applications. Now the next piece that comes into play on the selection of the system, once you get past the number of slots that you have on like a secure sync, the oscillator type is the power supply. And you think, oh well, a lot of these devices, don't they have the same power? Well, this is where, based on your need, is we have different options available to you. On the VersaSync, there isn't actually a power option. It's DC powered. But on the Secure Sync, we have options for both fixed DC power and then, fixed AC power, and our hot swap. And our hot swap allows for two power supplies in the unit that build in that resilience, so not just resilience at the reference and the signal, and we talk about that and how it combines, and resilience in the oscillator and holdover performance and such, but now talking about resilience in a basic piece, which is how you get power to it so that it's actually running. And so in the Secure Sync, we have the option for hot swap, and then you have the choice of your hot swap supplies. Now there usually isn't a whole lot of choices that you're making, because it's really, where am I putting this and what is the power I have available to me? But what's nice is you can mix and match. So let's say you had an AC mains input. Well, you could combine that, let's say, with a DC backup, if that's how it's coming in, or you can have dual AC, dual DC as well.
One thing to note, we do also have a fixed DC option as well. So fixed AC, fixed DC, and then the hot swap. For those of you that may be familiar with our old Secure Sync, that hot swap kind of gets us the AC-DC configuration that we used to have all those years ago, which works out well for customers that may be replacing older equipment with the newer equipment. It is able to be a drop-in replacement for power as well as I/O as well, the shared option cards and those things. I guess as we start talking about some of the finer details, one of the things that we want to end with is, at least on the Secure Sync VersaSync portion of choosing your timing solution, is some of the accessories, mainly the IDM suite itself that we have, and the 8230 AJ antenna. We receive lots of questions from customers, especially in today's day and age, now that we've all realized just how vulnerable GPS is, that people are wondering how they can maintain, or how do they know if they have GPS interference? What do they do when it's detected? How can we protect the timing signal that we're sending out into their networks, to their end nodes, all those things. So we have two options. They can be combined together. You can use the 8230 AJ, which is a drop-in replacement for our standard GPS GNSS antenna. The reason that we call that an AJ is it's a passive anti-jam antenna. It has a filter built in where it basically looks up at the sky in a cone. It ignores terrestrial signals from 30 degrees of elevation and below, mainly because that's where most jamming and interference will be derived from, our terrestrial sources. So if our antenna is ignoring those, it allows it to then be receiving, hopefully, all live, valid signals. And we can think of that like a firewall or a filter of sorts, because we're filtering out signals from areas that we maybe don't have much confidence in. And then at the same time on the unit, we can also run the IDM suite, which could be seen as more like a software firewall. It's now monitoring the signal and then making decisions based off of that. Dave, do you want to go into?
Yeah, so you think of the AG antenna. So the best way to prevent the interference is right at the source. Don't even let it come into the system, right? And the other piece that you explained very well, that you might hear the concept of horizon blocking, and that's really kind of what it's doing by doing that lower elevation filtering. But signal can still come in, and that's where the IDM suite comes in, because it can then do detection on the signal that's now come into the system, right? Looking for both traces of jamming that may still be coming in, or for effects on the data input, which would be spoofing, and then it can provide alerts into the system that can disable the GNSS input in order to then go to the other resilience, which is your other references that you may have coming into the system.
Or the internal holdover oscillator if nothing else is present.
That's right. Whenever you lose all your references, you just go and you go onto that holdover, that great holdover that you can get from our oscillator selection.
Which is why we spent so much time talking about holdover, because it's your last fail-safe before you have nothing. Both of those options are available with the VersaSync or the Secure Sync. Realistically, an antenna can be used with any GNSS receiver as well to add protection and give you that kind of peace of mind that hopefully you won't be affected by any sort of interference, which we should, I guess, clarify could be, accidental. There are cases where that interference could come from a noisy antenna next door, maybe not as always a malicious intent. So
coming back now, so looking at the Secure Sync and the VersaSync in the layered approach that we talked about, so now you can sort of picture that Secure Sync and VersaSync fit very well at that reference layer. Obviously, with the ability to take in multiple external references, GPS, GNSS, and those others, and then provide that down. But then it might be, okay, do I go directly into the distribution, like another device? Well, Secure Sync and VersaSync, depending on the number of outputs you need, the types of outputs, that may actually be your distribution source, or it may sit as your distribution element itself. For example, with our 6 option slots, and often we have outputs that have 4 on a single card. You could get 24 outputs on a single unit, which to me sounds like distribution, right? And you can chain those and get there. But where we go into very high accuracy distribution, very high accuracy links, that's where we kind of transition into our White Rabbit products.
Yes, it's a perfect transition, Dave. Thank you very much. So when we talk about White Rabbit, we're looking at sub-nanosecond timing. We're looking at the need of distributing picosecond level timing across any distance. Long distances, short distances. The benefit and the idea being that more accurate the signal can be from the reference layer or the top of the distribution layer, wherever it's coming from, to the end nodes, the more accurate it will be when it's actually consumed by whatever's going to be using at the other end. And the longer we can keep it accurate, the less error that will accrue over time. We won't get into too much of it today, but we talk about NTP, PTP, usually in microsecond level accuracies. White Rabbit allows to go picosecond over distances and then convert to PTP at the very end, which improves the accuracy to the consumers. The one, I guess I won't call it a downside, but one of the harder requirements with White Rabbit is the need for the fiber optic networking connections that are dedicated generally to White Rabbit timing from point to point. We have a team of experts here that can help design that out and talk through how all of that goes. Over some distances, it's plug and play. Over longer distances, there's a little more math and calculations that are involved to make that sub-nanosecond accuracy. But the beauty of it is if that sub-nanosecond accuracy isn't always needed, a lot of just bringing it up can give you benefits especially when we go into the types of devices and the number of outputs each of might have for different applications and use cases, and connecting them together.
Right, and one question we often get is sub-nanosecond, right? What do I need that? What's the purpose of that? So there are applications that are looking for the best accuracy that can get, the highest fidelity, and we have to think about the White Rabbit products and the White Rabbit protocol really is the ability to maintain the accuracy that's coming into the front end of that distribution, the front end of that device, which is coming from your reference layer or your outside signal into it, and maintaining that level of accuracy from point A to point B, or even to point C and D and E, through that distribution. And so you have to look at your entire error budget, and that error budget takes up what's coming on the input side, and then what you do with it on the end side. And so instead of using that error budget in getting the signal from here to there, you have left that error budget up for the rest of that application. And that's really one of the key elements that White Rabbit gives you, is the ability to maintain the fidelity of your time and frequency from start to finish of that White Rabbit link. Now, as a consequence of being able to transmit that and repeat that over time, it does require infrastructure that is White Rabbit capable. And that's a little bit of how we get into the different types of White Rabbit devices that we offer.
So we'll start with the Z16. Typically, we're looking at a Z16 when we need lots of White Rabbit or PTP network timing distributed out. That either will take in White Rabbit as a reference, or will take in a 1 PPS and a 10 megahertz from some device at the reference layer.
Like a secure sync.
Like a secure sync. It's a perfect transition. And then from there, it then distributes that out over the fiber network to other White Rabbit enabled nodes, where it's using a combination of synchronization and synchronization, words that I didn't think I would be using every day, but I do somehow, where we synchronize in time and frequency. So we're sharing the clock, and that's a little bit of how we get that sub-nanosecond accurate timing. The Z16 is very good at distributing lots of PTP or White Rabbit, and because we're very creative with naming, we can distribute 16 of them, which is why we named it the Z16. And then we can go into the Zen devices, if you'd like to then see what their differences are.
So we have the Zen devices, which are really let's say the endpoint devices. So we think of that as it could be at a front end where you have you don't have the need for that fan out that the Z16 gives you, but you need to maybe do a point-to-point link, or at the end of a White Rabbit distribution chain to convert back into some of the other signals, those legacy signals, right? The 1 PPS, 10 megahertz, iRig, but also network signals like PTP, and that's for consumption by the end device. And so the TPFL sits there at that endpoint to do the conversion back from White Rabbit into the signals or other network timing that then will be consumed by the rest of the system. We have a variant of that Zen device, which is our TP32, and that is sort of a combination of end device of a White Rabbit link, but then combines distribution for PPS or iRig out. So it provides 16 PPS, 16 10 megahertz, 16 iRig, not all at once, but through software selection that then allows you to distribute those devices without having to have an additional device just for that signal distribution.
And it saves on option card slots, because we would have to duplicate that with a secure sync with lots of option cards. So it is a benefit, and it's receiving White Rabbit directly. So it is then being the end node conversion. So devices that might need a PTP or an iRig or a PPS now are getting it from a more accurate source than up at the reference layer.
Right, and we talked about the distribution layer and the different the different ways those things can kind of look. And so you can combine these White Rabbit products in different links to match the kind of distribution that you need. And so let's say you have a site that has a lot of end nodes that you need to get to. Obviously then a Z16 makes a lot of sense. But let's say that you are only doing a site-to-site link. Well, maybe you don't need a Z16. Maybe you could have a TPFL that is doing that site-to-site link, White Rabbit link for you. And then on that site, then maybe you do need a lot of devices, and you can then chain a Z16 onto that. And as we discussed, part of the beauty of the White Rabbit protocol is maintaining that accuracy over all of those hops through the White Rabbit devices that allows you to have very interesting distribution setups that can provide not only the quantity of end user devices that you need to supply, but also things like the site-to-site resiliency that you can do. So, I have an issue at my site A that has my reference devices. I can fail over through the distribution chain with my White Rabbit devices from another remote site without losing the fidelity. Coming back to that error budget that you get through distribution, you don't take that hit with having to go to some remote site because you can distribute that with high fidelity from there through White Rabbit.
Yeah, and I think all of this, kind of to summarize it up, we talked about a lot of different pieces of the solution. Just imagine how the many and very different combinations of all those pieces that we could have, and they're all going to be very application driven. Each application is going to be slightly different. And then as we kind of touched on at the beginning, those applications might evolve over time as well. The beauty about the Safran Timing Solutions are that they can evolve with your applications and grow with them over time. We do provide free software updates for the products, 2400, the VersaSync, the White Rabbit products, which are field upgradable. So if there are new features that we add over time, new security improvements that we add, those can be implemented in the field, along with adding option cards to fielded units. So if your number of inputs and outputs increases, or you need a new timing signal, those can be added in the field to the secure sync. We can always add and connect in more devices as new maybe sites come up or new things arise. And as all of these topics are very detailed and technical, Safran has a great timing organization. We have the applications engineers here that are always happy to help design and provide the solution that best fits your needs and your application, keeping all of the kind of factors in mind. So
this configurability is great, and hopefully you'll be able to be armed with that information to kind of come into it with some ideas. But of course, we are here to help drive through that. We love talking with customers and helping craft the right solution for you. And now I'll turn it back to Patrick to help moderate the Q&A. I'm excited about this.
Oh yeah, you like answering questions?
I love answering questions.
All right, thank you both for a wonderful presentation. Now, while both of them get situated for our Q&A section, I would like to add that as part of our increased focus on customer experience, we've been creating a vast library of curated resources here for each one of our products, such as application notes, FAQs, and our support tutorial videos, which outline specific troubleshooting topics in video walkthrough format. All of these are available in our support hubs at the displayed link. And so at this point, we will start our live Q&A portion of the event. This is your opportunity to ask questions directly to our experts. So once again, I will pass it back over to Ron and Dave.
All right. Thank you, Patrick. Appreciate all the support. So now that we're diving into our live Q&A session, we had several questions submitted prior to the event. So we will start there, and then we will check in on some of the questions that were submitted live during the presentation earlier, and hopefully answer some expert questions about our products. So the first one that we wanted to start with was sent in before, and it was related to how the new products are compatible with old products. Historically now we had the SecureSync 1200, and now we have moved on to the SecureSync 2400. We've expanded out our product line with VersaSync and White Rabbit, as we talked about in the presentation earlier. The good news for us is that the 2400 and the 1200 are drop-in replacements, as close as we could to be drop-in replacements, understanding that customer applications might have legacy equipment installed that they then might have to transition out over time. There's some restrictions on when they can make those changes. So we wanted the 2400 to be able to fill that need as customers' uses and requirements need those devices. So from a look and feel standpoint, the web UIs are all the same. Obviously, the newer products will have features related specifically to the newer hardware, the newer functions that we've added to them. But when someone comes in from our prior products to one of our newer ones, we want them to feel comfortable utilizing it, understanding the configuration, the web UI, where to find different things, even the connections on the back. We've updated some, I know, with the antenna connections and stuff like that, but we tried to keep that as familiar as possible so that it would work with the old systems, but as well in the existing applications.
Yeah, this was a big push in going from the 1200 to 2400, is making sure that we can maintain the capabilities as they go forward. Ron, you talked about the look and feel. So that's really important, where customers have generated maybe documentation and such on how to use them. They've done trainings, and you'll come in, you'll look at a 2400, and generally speaking, you'll be able to immediately be able to use that in the same way that you use a 1200. And in compatibility, even with our option card sets that we have, many of the option cards are the same across, so they're just drop in between the 1200 and 2400. Obviously, going forward to the next generation, we did add a lot of new capability, new functionality, and so of course in those areas there will be differences between the older unit and the newer unit, but the real compatibility is in the interfacing, right? And so whether it's on the input side or the output side, and in those cases, if you're using PTP, using iRig, you have GNSS on the front end, using those in the same way, configuring the same way, they'll operate in the same way between the 1200 and 2400.
Yes, yeah. We make it an effort to not deprecate old functions while we add in new ones. We understand, especially there are certain applications that require some more legacy signaling to be present along with the modern newer signals of White Rabbit, PTP, NTP, and anything that might come out going forward in the future. So it's we started with a very general question. There's a lot of different elements to that question, but I think that provides a good overview of kind of the compatibility.
And like we'll say with a lot of these, with specific applications, when you get into the details, we're of course available through our support, through our applications engineering team, to go through your specific use case, your specific environment, to talk about transitioning from the old to the new.
Absolutely. So we'll do another question that was submitted previously. So this one was related to our discussion that we had with the IDM suite in 8230 AJ. The question was asking, does your timing solution replace GPS, augment GPS, or backup GPS? That's the first part. So we'll cover that, and then we'll go into the second part. So we're from our timing solutions, we're not necessarily replacing GPS. We are more backing up GPS. However, there is some opportunity in there for augmenting our GNSS receiver that's built into our products. Does support augmented GPS signals, so like SBAS. For the Asia Pac region, our receiver also supports QZSS, which is an augmented system to GPS. We're focusing mainly on timing for this Sync with an Expert webinar, but we do have some background, I guess, to say, because we use GPS regularly for the augmented side. When we get into backing up GPS, that's where we talk about, or we can have conversations about the holdover oscillator, how we can architect timing solutions with White Rabbit, with the ability to transfer time at sub-nanosecond accuracy or even nanosecond level accuracy over distances. That gives us an opportunity to say that if there's interference or something occurring at one location, if we can send timing from another location that may be outside of the interference zone over to the other one as a redundant backup, that's where we can look at the synergies between our products. Synergies in 2024 is a word that comes up, I think, a little too much, but I will use it here. And along with that, we have other timing signals that we can look at now and in the future, and with always the idea of redundancy, backup, and resiliency.
Right. So you can, that's all, exactly right. Is, we are a user of GPS and GNSS in our systems. Now, if you relate this to whether, what's the difference between, a time server versus just having a, GNSS receiver that you come out of, one of the key things you had mentioned was, the holdover capability to, as a backup, if GPS or GNSS, you were to lose it, either through an antenna problem or something more malicious like, jamming or such. But then you can also think of the other references that we can take in as complementary to GNSS or GPS. And those can come from other equipment that you're in control of, or it could be coming from an external feed that you might have. Let's say you're in a colo, and some other data center. You may have a timing feed that you can come in as a backup to an antenna feed that you have. The other thing that you can think of, especially when we talk about White Rabbit and the distribution capability, if you look at the number of GNSS nodes that you might need to maintain in your timing network, your timing distribution, you could look at things like White Rabbit to help you reduce that number by having the capability to bring in a timing reference from a remote location, a remote site, that gets you out of potentially an interference area like you were talking about. That can be complementary to that GNSS, even though it, from a sense, it could be GNSS on the other end, but you'd be complementing the geographic area of that GNSS with something from another area.
For sure. And then the second part of that question was, how does it perform in wireless indoor networks? It's an interesting question because GPS inherently is a weak signal, so it doesn't make it indoors very well. No. We've tested over the years. We have customers that have run into this, and so I think when we talk about wireless indoor, we're not looking for GPS as that. I think it rolls somewhat into like the backup that we were talking about just recently of bringing in a timing signal from somewhere else, or distributing the holdover time on your rubidium or your OCXO oscillator across the timing network. And then the wireless aspect of this question adds difficulty in there because wireless network transmissions inherently have negative impacts on timing performance as well. So it will depend on the application and kind of what the timing requirements are. If there are hard accuracies that need to be made, wired discrete timing signals are always the best. But that's not to say that maybe sometime in the future, as technology progresses, something might come up and go from there. I don't know necessarily if we fully answered that question, but
Well, I will say, there's a couple aspects to it, depending on what how the nuance of the question, right? So GNSS is a very weak signal. It's below the noise floor, and so it doesn't get into buildings, data centers very well, if at all, right? I will say that we have some lab benches here where we can just put an antenna on the bench, and it can receive it. The signal is dependent because it's actually relying on more multipath reflections to actually receive it versus actually live sky, direct to a satellite. And so that has an impact on the performance and such. The other piece that is coming about is there are new advances in wireless in Wi-Fi. So the new Wi-Fi standards are taking into account some timing elements, and things like 5G. We're doing timing from 5G. That is something that is coming, soon. It's not here necessarily yet in a deployable fashion, but these are all new capabilities, new technologies that we are watching and looking forward to take advantage of for our customers,
and hopefully integrating into our products that we have now. So
absolutely,
all that modularity and growth. So I think we'll go to a live question. We have a few. Thank you very much for all of these questions. So let's see. You know what? We had a whole segment on oscillators today. So I think we'll do this question about how long does it take to get OCXO versus rubidium to be disciplined to spec levels from cold startup with a good GNSS as a source?
How often do we get that question, Ron?
A lot.
A lot.
Yeah. Everybody wants to know the minimum amount of time required to get the spec sheet. And we've both been doing this a while now. I don't think either one of us ever has a direct answer to a question. It's always
it depends.
A yes or no, it depends. So I guess I will start with the data sheet definition of our spec and what that means. So if you have looked at or will look at, hopefully, our data sheet for our Secure Sync, our VersaSync, we do have a spec for accuracy as well as holdover performance. When we're talking holdover performance, as I think this question is referencing, our data sheet spec for both Secure Sync and VersaSync is after 2 weeks of GPS lock. So we say 2 weeks. That gives us a guaranteed amount of time that the oscillator has had time to lock to a stable signal. It's been able to warm up, as Dave was so helpfully discussing in the presentation today. Temperature is a huge factor on our holdover time, and it's something that we try to compensate for internally, things like that. So the oscillator needs time to warm up. It needs time to lock to the signal, make sure it's stable. The longer that you run it, the better the performance will be. Obviously, there is a limit to when you have the minimum amount of time. 2 weeks is a safe bet. I know we have discussions regularly because applications sometimes always can't run for that full 2 week period, or they have power requirements that mean they have to shut off, or any of these things. And so then that's when the debate starts of what is the actual minimum amount of time?
Well, and what factors into that, right? I mean, you mentioned a couple, there's some base characteristics of the oscillator that come into play. So all the oscillators have a retrace period where they come up, and you know what, it happens, they're not the same frequency as when you turned it off, and so you have to allow that almost, basically a warm-up period for it to kind of stabilize. And the different oscillators have different lengths of time where for that to take place. Rubidiums actually take a little bit longer than the crystal oscillators like our OCXO, our low phase OCXO, or our TCXO. And then you have things like just stabilizing the synchronization. Just the algorithm itself needs some time to stabilize. There's other aspects like holdover that come into play. So as part of our disciplining algorithms, we are learning during that
synchronization period. And so we are learning what is the optimum frequency to for the reference, and then what would that be when we go into holdover. So, obviously we are correcting for phase and frequency errors. That's what we do for synchronization, right? And as part of that, obviously we are adjusting that frequency of the oscillator to track the input. And so we are purposely setting the frequency off, not by a lot, but enough to steer. And so when you go into holdover, we have to bring it to what we believe is the real value in order to kind of maintain where we are for as long as possible. And so there's a learning period for that in order to do that. And then the other big piece is the reference. Now, this question was specific on, GNSS. You get another reference, then it's based on the quality of the reception and things like that. So,
and I will say, when we are talking through different applications and the needs and requirements of them, typically where we will, kind of fall back to in an ideal situation or, our starting reference kind of architecture, applications that are able to be more stable, to have a stable temperature, powered up for longer, those sorts of things, that factors into, the oscillator type that we select and where in the distribution reference layer, where in the architecture they go. Typically when we're doing, let's say, an NTP network, we want rubidiums at the stratum 1 in sync to GPS. And then, downstream, because they'll be receiving network timing, maybe not the most stable at all times. That's where we'll look at the OCXO, as it's a little more forgivable than the rubidium in that input reference. So all of these are factored in. I don't know if there's any one hard answer other than the idea behind our data sheet is to make sure that you have the most amount of time on the oscillator and get that across, especially for rubidiums, which are a little more sensitive to some of those inputs.
Right, and that's of course to get to the specifications we talk about on the data sheet. If your specifications are looser than that, then there may be some variance to the amount of time. And I will point out, you talked about temperature. I would also say that the spec is based on a stable environment as well.
Yes,
so
absolutely.
All right.
So I mentioned NTP and PTP. I think this is a great transition to the next question. If you're only using NTP or PTP from the network ports, does phase noise matter? So this is an interesting one because my initial reaction is that if you're using NTP and PTP, you're not necessarily worried about phase noise. However, and correct me if I'm wrong, but that's not to say that one part of your application isn't worried about phase noise. So one thing to think of is that because of the high configurability and modularity of our timing products or timing solutions, is that on one end, you could be feeding a 10 megahertz into an application or 1 PPS into an application that is very sensitive to phase noise. So in the presentation, you mentioned radar applications, for example. But that's not to say that there aren't other timing devices or timing end nodes in the network or in the application that don't necessarily care about frequency error or phase noise, but they still need some sort of timing reference and they have NTP or PTP. So in this case, part of your application needs that phase noise requirement. The other part doesn't. If you run a secure sync, for example, with a low phase noise oscillator for the I guess the more stringent requirement, then you can also still utilize the network ports for timing to other areas of your application.
Yeah. So I mean, the quick answer is if you are only using NTP or PTP, and that's what's going to the end system, and that's all you're doing, then no, you don't have to worry about phase noise. But often that's not necessarily the case, right? So you may be using the systems, time servers, for multiple use cases. One of those might be NTP or PTP. And then when you look at the whole distribution, let's say you're using NTP or PTP, maybe not NTP, but PTP or White Rabbit for your distribution, you're then recovering that on the end node or the recovery point. That system the outputs from there might be 10 megahertz or something, and then phase noise might come into play for what you're outputting from the end of the distribution layer into your end devices.
Yeah, for sure. So always a complex answer.
Yeah,
But,
everything timing, right? You know.
That's why we're here, right? Okay, we have another one. Do you need to use the IDM suite via the web interface, or are there software packages available like there were for the T-Sync PCIe cards to poll signal status? So I would like to separate this slightly, and I think it's just a clarification point. The T-Sync PCIe board shares the same timing platform as the Secure Sync and VersaSync. They still have the ability to poll satellite data. So you get signal status, you can get your fixed mode, the survey progress, all of that. That is information coming directly from the receiver. The IDM suite that we talked about is software also running on the timing solution or the timing platform that is also receiving all of the same GNSS data that we already had API calls to access. And it is doing, I will say, magic, some sort of magic behind the scenes to detect if it's seeing interference. So it's not a one or the other. The GNSS receiver is the central source of all this data, and we have different elements in the system that are using that data in different ways, providing it out different ways. For the original question, the IDM suite is a web-based GUI to see the status, but that's only for visualizing it. It does integrate well into our SNMP traps, our email notifications, our general alarming system overall, to have ways to alert users that, hey, something might not be right. We don't necessarily know what it is, what the cause is, but looking at the data that the system and the receiver is providing us, something needs your attention.
Yeah. So it's embedded. So it's embedded software running on the system, and you said through the web interface you can see the status and you can do some controls and such. But it's fully integrated within the system that it's enabled through software license, and then you can use that to protect the system that it's on. But you can also, we've done a few things where you're actually using it as sort of a sensor. Yeah. Where in addition to protecting that system, you can provide notifications of IDM interference events out to monitoring systems to help control other aspects of your system, or your total environment, because you may have other equipment that is using GNSS that doesn't have its own interference detection, and so you can utilize the IDM suite on some of our products, both there and to know the environment for other applications.
Definitely, yeah. So I think the big point here to highlight is we still have that legacy functionality. I'll call it legacy functionality, but we still have the functionality and love of our timing solutions, and we just keep adding and building on more as needs arise. So I think we should go back to maybe one of the questions that were submitted prior, which we got a lot. Let's see. All right. So how does better, more accurate time distribution benefit data centers? Do you wanna take a start?
Well, do I start with like everything else? It depends. Well, it really depends on the application you're using, right? Yeah. So data centers, that market, that use case, has a variety of different functions that they're doing. Let's say it's big data with distributed databases and things like that. And so improved timing can improve the time it takes for eventual consistency of your databases. Let's say you are in a data center doing time tagging of information like a financial, in the financial sector, right? Your ability to have a more accurate timestamp of when events occur, when news feeds are coming in, when actions are happening, financial applications are happening, that allows you to have better awareness of it and better segmentation of those events between each other. So the granularity of that is improved.
Okay.
In other applications, it might just be for auditing and logging,
Mhm.
and there, even there, it might be, I don't need super accurate time, but I just need to know that every piece of data, the time that's happening at that timestamp
Mhm.
is related to every other timestamp that I have that might not be getting it from the same exact source there. It might be in another data center, it might be in another rack in that data center. And knowing that your distribution is reliable, it's accurate enough,
Yeah.
that allows you to relate all those events to each other.
For sure. All right. I think.
I think we're.
Yeah, Pat. I think we've hit our time at 11 here.
It's too bad. I mean, I love answering these questions. We could
we
could probably
keep
go for a
going.
lot longer. Maybe not for this audience, but
I think. I think they're waving us off now. So thank you very much for the questions pre-submitted and submitted during the presentation. And at this time, we'll hand it back to Patrick Bark to close us out and end the webinar today. Thank you, Dave. As always,
thank you, Ron.
Appreciate it.
All right. Thank you, everyone, for attending our event. I know some of you didn't get your answers to all of your questions there. So I have published our final poll for you, which is asking if you would like to be contacted by someone from our team following the event to discuss the best solution for you. So please feel free to do that. We also have on the screen right now is displaying options for our feedback and our contact details, as well as our online store URL for anyone based in the US. So if you would like to take the initiative to contact somebody from our team, please feel free to do that there. Otherwise, judging by your answer to the poll, we will get in touch with you. So thank you again for attending. We really appreciate it. We hope you learned a lot from this webinar, and we learned a lot from everybody that participated in the polls. So thank you and have a wonderful day.